Hello everyone, good morning, afternoon or evening, wherever you are. My name's Dave Chapman from First Light Fusion, and I'm going to be talking to you today about investigating the role of transport in uniaxially-driven conical fusion targets. Before I get going, I just want to acknowledge the efforts of the various team members at First Light Fusion who've contributed to this work, as well as those of my collaborators. I also want to thank the organising committee for the invitation to speak today, and I think despite the obvious difficulties, it's proving to be pretty successful so far, and I've been really pleased to see so many excellent talks have been made accessible. So here's the outline of my talk today. I'm going to start by giving a brief introduction to the experiments carried out by Derentowicz et al., which are the primary source of motivation for this work. This will lead into a discussion of some of the ongoing work we're doing with regard to establishing sensitivities of the simulations to the many unknowns in the multiphysics model, here focusing specifically on transport. I'll then share an update on the work we've started to build a new standalone capability for providing more accurate transport and microphysics data to the codes via the TRAMP and SPK codes. The path forward will be discussed, and I'll cover some of the points that we believe will be necessary to get us towards a more predictive capability in the future. Finally, I'll briefly summarize and present the conclusions that we've drawn so far. So the experiments carried out by Derentowicz et al. In '77 are particularly interesting to first light, as it's one of the few examples in the literature of a fusion system driven in a geometry aligned with our core reactor technology vision. That is, along a single axis with a strong planar shock without using lasers or particle beams. The basic outline of the experiment is shown here on the left, wherein a copper liner is imploded under the action of high explosives to produce a central downward traveling max stem that goes on to impact a fuel-filled conical cavity in the gold anvil. The drive produces a flat, high-pressure region in a 100-micron plastic cover slip that unloads into the cavity, driving a collapse that leads to conditions which are conducive to fusion. The reported yield is on the order of about 10 to the 4, with up to 3.5 10 to the 7 neutrons claimed by the authors. Unfortunately, there's no experimental data given in their papers, so we really only have the numbers to go on. Modeling of this problem is actually a highly valued benchmarking case for our in-house radiation hydrodynamic simulation capability due to the wide range of physical phenomena that are at work in the target. It's also become a standard case that we use for interacting with our collaborators. So far, we've been able to model the initial dynamics of the explosive drive to reach quite close agreement with the reported radius and the velocity of the max stem. But so far, we've also been unable to substantiate the reported yields. The series of pictures I'm showing on the left show snapshots in time of a simulation of the max stem formation, which impinges on the fusion cone package shown in the zoomed in section in the upper left-hand part. Plots of the max stem velocity and radius as a function of liner angle are shown on the left, where we see generally very encouraging predictive results from both of our codes. The black points are the experimental data, and overlaid are the results of First Light Fusion's 2 in-house simulations tools. These are HyTrack and Code B. Importantly, the conclusion from these results is that the implosion of the fusion cone can actually be quite well decoupled from the remainder of the simulation, and this enables a high-resolution idealized model to be constructed for the implosion of the fuel itself. This is what I'm showing here. This is the idealized component of the model that we've used throughout the simulations campaign. And what I have found is that by using our default suite of multiphysics options, we tend to underestimate the target performance by roughly a factor of 100. I'm sure everyone watching who's ever simulated ICF before is pretty much aghast, because typically we massively overestimate the performance of the target. In this case, it's very much the opposite, and we're trying to understand why. As I've said before, since we know we can be confident the platform can be decomposed approximately around the drive of the fusion cone, the simulation can be initialized with a flat, uniform shocked state in copper at around 13 eV in temperature and almost 3-fold compressed. The zoomed in part of the schematic shows the cone tip, which has got a radius of curvature of 10 microns added to represent the sharpness of a typical manufacturing tool. As you can see, we've gone down to quite high resolution through the use of HyTrack's AMR capability, with the minimum cell size being roughly 1 micron. The video that I'm showing here on the left-hand side gives the density and ion temperature maps for the default configuration of the idealized target, which produces about 100 neutrons, i.e. about 100 times fewer than those values reported in the original experiment. The shock transmitted into the fuel that you see gets turned at the corner, setting up these fast reflections normal to the wall that speed in and collide on axis, then reflect from the cone wall before stagnating into the tip, reverberating around in the cavity and being imploded and heated. These shocks are followed by a pair of plastic jets which are emitted from the corners, and you can see that these go unstable quite quickly as they drive into the heated fuel, and they flatten out to act as a piston, and that's what really produces the majority of the yield as it's being compressed and heated. As you can see from the two time history traces I'm showing, these are the plots in the middle, we get reasonable convergence of the cumulative yield and the burn-weighted ion temperature at the resolution that we use, so we can be quite confident in the numbers, given the setup of the simulation, of course. So that really begs the question, what could be causing such a vast underprediction of the yield? Well, if we plot the cell trajectories of the PMMA and anvil material on the rho-t plane, then we can see that the states produced cover quite a wide regime. In particular, the densities and the temperatures are conducive to strongly coupled ions and degenerate electrons, i.e. quite non-ideal states. And this is where collisional transport properties of such materials are known to have significantly large uncertainty. So to understand the importance of these uncertainties, we've performed a basic scaling factor analysis where we look at the different components of the multiphysics model and uniformly apply a constant that we are looking for correlations to the target performance. Shown on this slide are the results for the scaling factors applied to the electron and ion thermal conductivities and also the electron ion energy exchange rate for both the fuel and the gold anvil. I should say that the thermal conductivities that we're using are those of the Lee Moore and Stanton Murillo models, respectively, and the equilibration rate comes from the F-sum rule approach that was first developed by Hayzak et al. It's pretty clear from these that the largest impact on the yield comes from reducing the electronic conductivity of the fuel, and this increases the yield by roughly an order of magnitude. We can also see that increasing the conductivity by only a factor of 2 almost triples the yield. Maybe this is unsurprising. However, I was surprised to find out that there's not a great deal of effect that comes from fiddling around with the parameters of the anvil. Also not shown on this slide are those of the jet material itself, and that also showed quite relatively weak impact. The next largest influence I did find was that came from the turning down the equilibration rate, because this helps to maintain higher ion temperatures and therefore higher thermal reactivity rates. I think the overwhelming message from this slide is that it's good news because obviously the thermophysical properties of gold particularly are of far more uncertain than those of simple materials such as deuterium. Oops, wrong way. Aside from the values of transport coefficients, there's also numerous other uncertainties that exist in the multiphysics model. Given the importance of electron conduction shown on the previous slide, I thought it would be clear relevance to also show how the configuration of the conduction operator itself can affect things. So as an example, the cartoon on the left shows the standard conduction stencil we use in the codes where the fluxes, which are denoted Q, are computed on the cell faces -0.5 and +0.5. The expressions in the red boxes show how we construct the effective thermal conductivity, which appears in Fourier's law as an energy source in the Hydro equations. And the terms highlighted in blue are effectively all free parameters. The two plots on the right show some of the functional forms that we can use to apply the interpolation between the regular and flux limited forms of the conductivity in the left-hand part, and the interpolation which evaluates the cell-centered quantities to the cell faces. By this I mean things like the temperature and the density, and then the values of the tabulated conductivity we get from those thermodynamic conditions. So the latter is actually of special interest here because there are lots of competing views about in the HEDP community about what you should use. So for example, the paper from which we implemented the super time stepping method in our conduction evolver advocates a harmonic mean, whereas an arithmetic mean is probably a more natural choice for a continuous variable. Whilst we do find that all of these methods converge for cells which are embedded, for example, in the same material, there is a substantial uncertainty about how accurate any of these approximations are for treating the material interface itself. So the influences of different choices for these options on the previous slide are now shown here for the electrons in the upper row and the ions in the lower row. The general conclusion I found is that the softer flux limiter interpolation tends to enhance the yield a bit as it quenches conduction early relative to harder switch types, such as the exponential or min-cap methods. I've really encountered some code robustness issues here, so I can't get a complete picture. Nevertheless, given the trends, I think it's fair to say that it's going to be unlikely that it affects the enhances the final yield all that much. The The single largest change that I can say I've found is due to changing the cell center to cell face interpolation method, specifically for the maximum heat flux that goes into the conduction of the flux limited conductivity. And that's from changing it from an arithmetic to a harmonic mean. This again results in a single very strong pulse of neutrons from the stagnation of the shock coming into the cone tip. And the reason for this is that the harmonic mean selects the lowest of the two values, in this case, the lowest maximum heat flux. And that goes into constructing the flux through those two cell interfaces. And that basically means that the conditions of the anvil, which is cold and high density, are those which dictate the value of the flux limited flow that goes through that. The result of this is that there's a very artificial insulation of the fuel in the cone tip, which remains hot and therefore gives out quite a bit more fusion. Overall, I think it's probably fair to say that we really have to change the model quite dramatically in order to, and potentially also very unphysically, in order to get substantially higher yields than we're getting from the base model. Furthermore, the sensitivities that I'm showing here, I think, are pretty indicative of the fact that we actually need a non-local thermal conduction. So since the strength and the character of the shock is such an integral part of the operation of this target, we've also investigated the influence of physical viscosity, which can that's just been receiving a lot of attention in the ICF community recently, particularly for spherical implosions. So on the left-hand portion of the video that's playing here, I'm showing the ion temperature throughout the simulation, comparing the inviscid on the left to the viscous configurations. The most notable change is that at the first axis reflection, the viscosity of the plasma becomes large enough through high temperature, because it scales like T to the 5 halves, to produce a significant damping and frictional heating of the shock, which then goes on to change the timing and subsequent bounces, which ends up reducing the yield from the cone tip. This is shown for clarity in the upper plot to the right-hand side of the video, where you've got the inviscid case in orange and the viscous case in blue. We can see that on the right-hand side of the video, we've got the Prandtl number, which is essentially the ratio of the momentum diffusivity to the thermal diffusivity. And this approach is about a value of 0.3 or so they're pretty competing with each other. During that first reflection from axis, it remains relatively high around the shock for the first bounces, but it drops rapidly thereafter. And what this implies is that whilst the plasma viscosity does affect the initial shock structure, and it is actually conduction that dominates the remainder of the fuel energetics during the cavity collapse phase. So interestingly, we can see that by turning up the viscosity quite a lot, by about 10x, we can actually increase the yield, despite the initial contribution from the tip being almost, well, completely removed. This is because the incoming jet structures that I showed earlier, they're so strongly diffused that they actually spread out a lot more, and they become a much more efficient piston for compressing the remainder of the fuel. So another thing we've looked at is the kinetic effects, because the fuel is very low density. It starts off at a pressure of 1 bar. And this may be important because the ion mean free path is probably sufficiently long such that a local Maxwell-Boltzmann distribution can't be maintained throughout the simulation. And whilst this does have some important connotation to factors such as the heat flux itself through non-local effects, these are actually beyond the scope of the present work I'm presenting. However, something that does affect the simulation much more directly is the reduction in the thermal reactivity of the plasma, which is known to drop off very rapidly with increasing Knudsen number. For clarity, that's the ratio of the mean free path to the characteristic scale length of the system. So we've implemented the Albright-Mollweg reduced kinetic model for the ion distribution function, shown in the top equation here. And this gives a form that we can use to plug into the second equation, which is this fairly nasty looking expression with 3 nested integrals. This enables us to compute a table of reactivities indexed by ion temperature and Knudsen number that we calculate on the fly. And we can show that the results are in very good agreement with those taken from Hoffman et al. 2015 Physics of Plasmas paper. We can see that with the big blue arrow indicating increasing proton Knudsen number, that the effect of damping the reactivity is extremely strong. So the plots on the right show heat maps of the volumetric neutron reaction rate before and after the shock hits the cone tip. The top row gives the Albright-Mollweg results, and this shows correlations with the shock structure that can be seen more clearly when comparing to the Knudsen number, which is plotted in the middle row. In contrast, the standard Bosch-Hale reactivity does not really show any form of shock imprinting. And here the blue regions in the Knudsen number maps indicate regions where we have NK greater than 2. And for this, I'm manually setting the yield to 0 because the model is essentially broken down at this point, and we don't expect any real serious contribution to the reactivity. Overall, the effect is to further decrease the predicted yield, with values kind of depending on configuration being up to about a factor of 10x reduction. So the conclusion from this work so far is that the accuracy of our microphysics models is probably the largest handle on the accuracy of our simulated yields. So in order to tighten this aspect of our multiphysics model, we've begun working on a new standalone capability for transport and microphysics, which we're stylizing TRAMP. And this is driven by Imperial College's SPK opacity code. We've also built TRAMP to specifically address the inadequacies of our existing tables, which are particularly in the warm dense matter regime, and to incorporate the detailed ionization equilibrium information that we get from SPK. So here I'm showing an example of PMMA plastic, which was used in these simulations to represent the cover slip material. And for ideal plasma conditions, we use the Apfelbaum model, which is essentially just an improved relaxation time approximation, similar to LEMUR. Its main advantage being that it doesn't require an ill-defined Coulomb logarithm, and it builds in electron neutral scattering and various other mechanisms for weakly ionized plasmas. In the warm dense matter regime, we use the well-known Ichimaru-Tanaka model. This allows for a much improved description of strong ionic correlations with the collision operator and the kinetic equation. And this is also fully convergent in both the long and short wavelength limits and is generalized to arbitrary electron degeneracy. The IT model is blended smoothly with the Apfelbaum model as it becomes inappropriate under weakly coupled conditions and is quite significantly more computationally expensive. So we really don't want to evaluate this when we don't have to. Finally, in the solid phase, which is denoted by the black curve in the central plot, states below that, I should say, we use a modified variant of the Simon-Bloch-Greniason model, which includes an umklapp scattering contribution for materials for which such a function is appropriate. And this is used exclusively below the material's melt curve. So some of the early output from TRAMP is shown on this slide. It's two rather challenging test problems. Firstly, on the left, I'm showing the electron thermal conductivity of strongly compressed hydrogen at a density of 10 grams per centimeter cubed as a function of temperature. The purple diamond-shaped points here are pretty well reproduced across the whole board, and these correspond to the DFT-MD results obtained from Lambert et al. The second case is for a solid-state isochore of aluminium from room temperature all the way up to the ideal plasma phase. In this case, the melt transition is captured quite well, but we lack any validation data to really constrain how the model should be behaving around the transition to the ideal plasma regime. In both plots, the vertical dashed line roughly delineates the strongly coupled phase to the left from the weakly coupled phase to the right. So you can see that we're doing a pretty decent job over quite demanding conditions here. Improving the ion-ion and pseudopotential that we use and generalizing the code further to multi-component structure factors, for example, is something I'm working on. And I'd be very thrilled to collaborate with anyone who's interested to work with me on this. Still, as I said, I'm very encouraged by these results, and I believe that with them, we can close down one of the main sources of uncertainty in our predictive modeling capability. So just to tell you a little bit about the ongoing work we've got, some of the possible multiphysics improvements that we're going to need for a much more enhanced predictive capability. The ones from this work, for example, are, like, as I said, a non-local transport option, as I think it's been fairly clearly shown that local flux limited diffusion appears to be inadequate for particularly this problem. So we might go to something, for example, like SMB. The improvement to the physics and also the numerical robustness of the TRAMP model for making large scale tables for arbitrary materials is something I'm working on actively. And we're also looking at making the equation of state model consistent with SPK and TRAMP. And some of you who may have seen Adam Fraser's talk on Tuesday would have seen the initial work that he's been doing to pursue that goal. Aside from that, and next on the list in our never-ending quest to make the codes better, is we're currently implementing a multi-group radiation transport package. And this is really so we can potentially capture any radiatively driven wall ablation that's produced from radiation emitted from the hot copper shock, and the potential possibility of adding high Z admixtures. Potentially that might improve the yield and get us closer to matching the experimental claims. And also something like mass diffusion, or the associated enthalpy transport that goes with that. I believe that might be quite important for especially getting the jet breakup structure that goes in to drive the cavity collapse. That's going to be very challenging because HYTRAC is a front tracking code, so it's not very naturally incorporated within that code structure. Also, existing AMR is going to need to be improved, and HPC scalability, and we're going to need this if we want to do some of the non-idealized modeling that really captures fully integrated simulations of these experiments. Potentially also we might want to look at MHD and XMHD effects, particularly trying to capture self-generated Biermann fields and some of the magnetized transport that goes along with that. So to summarize and conclude, I've shown you a detailed sensitivity study, or the beginnings of one at least, for the Derentowicz fusion cone type experiments. These experiments report neutron yields mostly on the order of about 10 to the 4. And so far, despite our best simulation efforts, we can't substantiate these claims. And we get roughly 100 neutrons or thereabouts, maybe a little bit more, out of the majority of our simulations. We find that thermal conduction makes the biggest difference, principally through the uncertainty and electron thermal conductivity of the fuel. Although there is some evidence for also non-local effects being important, and these presently aren't implemented in HYTRAC. There's something we want to look at. Real plasma viscosity effects were examined, and we found that the internal shock dynamics in the final fuel energetics can be affected by this. The reactivity reduction in the high Knudsen number flows also reduces the yield by roughly a factor of 10x. So we believe that this could potentially be indicative of more non-local effects that might need to be taken care of. So to address the biggest uncertainty, we've developed a new transport and microphysics package called TRAMP that we are hoping will drive down the uncertainties that lead to the largest part of where we're uncertain in the modeling. And this is something that it's ongoing. We also told you about several new components of the multiphysics model that are being developed to further HYTRAC's capabilities. And to cap everything off, I'd just like to say that we welcome any collaboration in understanding this experiment and other ICF-related problems. So with that, I will thank you for your attention and say, please do get in touch and give me any questions that you want in the speaker chat.